Welcome to Class 3. We're going to be talking about public health surveillance with some examples and the importance of evidence and data sources in epidemiology. To calculate a lot of the rates we've been talking about in this course so far, you need a population for the denominator. So where does all that data come from? Vital registration systems are one of the important sources of data used in epidemiology. This map shows vital registration system completeness and quality by Vital Statistics Performance Index scores from 2005 to 2012. This is a little bit old, but I looked it up and it really hasn't changed that much in recent years. You can see a lot of the countries in sub-Saharan Africa don't have vital statistics because they don't have an established national system. The vital registration system in the United States was fully established around 1930, but if you were looking for data from the Democratic Republic of the Congo, for example, you wouldn't be able to easily access national birth registries or information about marriages, divorces, etc., because they don't have a national system for recording that information. In some places, a birth may only be registered when someone needs official documents of another type. And that can cause less accuracy because the person may not know how old they actually are. So people may have to estimate their age when doing paperwork later in life. Household surveys are really helpful in situations where the data isn't standardized across a country. People will go door to door and ask women how many births have occurred in their household, how many deaths have occurred. And that information is often what's used for life tables, which were mentioned in the previous class when I talked about survival analysis. Random digit dialing is an example in addition to household surveys going door to door that used to be used for collecting demographic information. It used to be a problem because not everyone had a phone. So if you were doing random digit dialing in a community, you would be excluding all of the people who were marginally housed and don't own a phone. But now that's less of an issue, but still something to consider if phone surveys are used to collect information about a population. Death certificates are one component of vital statistics that can be helpful for epidemiology, but it's important to note that death certificates are not always filled out correctly, and there's many sources of inaccuracies in death data. For example, there may be political or social or cultural influences on how the death certificate is filled out, and people often don't get training on how to actually fill out a death certificate. So there also may be inconsistencies between different people in completing the death certificate. On this slide, I give the example of a coroner may guess someone's ethnicity if they don't have anyone to ask. That would be an example of how inaccurate information could get introduced on the death certificate, because if a coroner is just looking at someone saying, I don't know, they don't look Hispanic, you're going to get some inaccuracies there. Comparisons of census data over time are helpful and can be used to estimate survival rate, because if you have census data from different years, you can see how the population increased or decreased. But this is not only influenced by mortality, it's also if people are moving into the area or out of the area. Population pyramids show the age-sex composition of populations. The convention is for males to be on the left and females on the right. So you can see in these two examples from the US on the left and Uganda on the right, Uganda has an extremely high fertility rate. It's a growing population. So you get this nice pyramid shape to it where there's far more young people than there are elderly people. When I lived in Uganda, I found it shocking how when you met an elder, a lot of the time they were like 50 and everyone would be like, oh wow, that person's really old. Because the population there is just so young. There's very few people over the age of 50. In the US, on the other hand, you can see our population is staying about the same. So that means that between people moving into the United States and our fertility rate, our population is not changing that dramatically compared to Uganda. If you start to see a population pyramid that's upside down, shaped more like a tornado instead of a pyramid, that would indicate that the population is going to shrink because there's fewer children compared to the number of older people. Population pyramids are helpful both to compare different countries, and also you can show how a population is changing over time by comparing its own population pyramid with a serial comparison over many years, and to evaluate achievement of population level health goals like the Healthy People 2030 objectives. When you're looking at population pyramids, it's helpful to consider mean, median, and mode, the measures of central tendency. To review, mean is the average, median is if you lined up all the ages in a row, it's the one in the middle, and mode is the one that occurs most often. The median age divides the population into two numerically equal groups, so half the population is younger and half the population is older. It's a single index that summarizes the age distribution of a population. It's important for us to be aware of the age distribution of a population because age differences make it difficult to compare diseases or other health outcomes between countries. For example, we can't compare Uganda's crude death rate to the US crude death rate because Uganda's crude death rate would look a lot lower since the population is so young. While a country like Japan is the opposite. They have a very old population, which we would expect to have a high mortality rate, but that's influenced by the fact that so many people there are elderly. To make comparisons between two populations that have a really different age distribution, we need to use adjustment, which we'll be talking about shortly. Here's a practice question. Look at these two population pyramids and tell me why we can't compare them directly. So on the left, this is comparing Alaska and the US population. And on the right, this is the Alaska Native population and the US population. So this is kind of a trick that it's only the Alaska Native population, not the entire population of the state of Alaska. We can see in 2020, the largest group for Alaska Native people was 5 to 9-year-olds, followed by 10 to 14-year-olds. The state of Alaska actually has a pretty good pyramid shape going on, showing that there's a growth in the population, which is different from the US population overall in 2020. You can see the gray line goes in a little bit at the younger age groups because there's less of the very young age groups in the general US population. The population pyramid on the right is from the Alaska Native Tribal Health Consortium's Epidemiology Center, which has a lot of great local data. The epidemiologic transition is the change in structure of mortality as the age structure of a population changes. When we were looking at that population pyramid of Uganda, that's typical of what you would see in a developing country. And over time, you often will see a shift towards what we have in the United States, where the fertility rate is much lower and is approximately at replacement population. So the population isn't actively growing anymore. With the epidemiologic transition, we typically see a shift in mortality cause from infectious diseases to degenerative diseases with older populations. Because many of the deaths in developing countries are children, they tend to be infectious diseases and injuries, whereas in older populations, we tend to see more people dying of heart disease and cancer. Being able to make comparisons between population health data is important to evaluate the health status of the population you're working with and to see how it compares to the broader population. To do this, we can use either direct or indirect age adjustment. For direct age adjustment, you need age-specific mortality rates for exposed and standard populations. And for indirect age adjustment, you need the age structure and deaths in an exposed population and age-specific rates from a standard population. Direct age adjustment gives you a weighted average of age-specific rates, and indirect age adjustment gives you a standardized mortality ratio if the outcome of interest is mortality, or a standardized morbidity ratio if the outcome is an illness. This is an example of the difference between the crude and age-adjusted death rates for the United States from 1960 to 2020. You can see before the pandemic, the age-adjusted mortality in the US was steadily declining, but the crude death rate was declining less overall before the pandemic. That reflects our aging population because If our mortality is high, but our age-adjusted death rate is going down, it's likely because more older people are dying. And then at the beginning of the pandemic, you can see there was a sudden dramatic increase in both crude and age-adjusted death rates. The age composition of a population can greatly influence the crude death rate. Most deaths tend to occur in people over age 70, so a population that is aging will naturally see an increase in the crude death rate. Crude death rate can be misleading if the age distribution of the population has changed a lot over time, or if you're comparing two populations, which is why we use age-adjusted death rates for comparisons. It's important to note that age-adjusted death rates using different standard populations are not directly comparable. You need to adjust for each comparison you want to make if the data was already adjusted using different standard populations. On the left, you can see that the deaths from COVID-19 for those aged 75 and over were dramatically higher than for other age groups, and that was followed by the 65 to 74 age group. COVID-19 data is a good example of where if you were just looking at age, it seems straightforward that that's the whole pattern of what's going on, that elderly people are dying at a much higher rate than younger groups. But it's only when you break it down by race and ethnicity that you see it's not evenly distributed. On the right, you can see the rates per 100,000 people in the population are much higher for Hispanic, Alaska Native American Indian, and Pacific Islanders compared to white people, Asian people, and to a lesser extent, Black people. This shows that while it's important to break down data by age, it often doesn't tell you the whole story. So it's a good idea to look at the data from more than one perspective to try to get a better understanding of what's really going on. In data that wasn't adjusted for age, there were some periods where the death rates for white people were higher or similar to some groups of color. But once they're stratified both by age and race and ethnicity, it becomes apparent that white people have lower death rates than people of color. This reflects an older white population in the US overall and higher rates of death across all age groups among people of color compared to white people from COVID-19. As I mentioned before, an age-adjusted death rate is the weighted sum of age-specific death rates. Direct age adjustment allows you to compare two populations, but it's important to note that this is a technique that uses fictitious rates. So you wouldn't use this information for program planning or public health resource allocation. It's just for the purpose of making comparisons between your two populations. For direct age adjustment, you ideally want to use a population that's similar to the population being studied. The age distribution of the standard population used is important because it determines the weight given to each age group in the adjusted rates. If the population pyramid looks like a Christmas tree, it will give more weight to younger ages. But if it looks like a tornado, it'll give more weight to the oldest age groups. Direct age adjustment uses a standard population, which we're going to create in this example by adding the two populations together. We add the total population from 2004 to the total population from 2024 to get our total standard population. Then we do the same thing for each age group, adding the 2004 population of 30 to 49-year-olds to the 2024 population in that same age group to get the standard population for that age group. And we continue that for each age group. Next, we find the expected deaths using the 2004 rate. We multiply the 2004 rate per 100,000, which was provided on the left, by our standard population we just created. That gives us 9,600,000, which we divide by 100,000 to get 96. We do the same thing for each age group, multiplying the 2004 rate per 100,000 by the standard population to get the expected deaths using the 2004 rate. Then we follow the same procedure to get the expected deaths using the 2024 rate. We then add up the expected death rates using the 2004 rate to get the total deaths expected in the standard population, and do the same thing for the 2024 rate. For the age-adjusted 2004 rate, we divide the total deaths expected in the standard population by the total artificial standard population we created. And we do the same thing to get the age-adjusted 2024 rate. This example shows why it's important to not use crude mortality rates to compare two different populations. You can see the age-adjusted mortality rate in this example is reversed in the sense that we calculated an age-adjusted 2004 rate of 124.3, but the crude rate from 2004 was 96 per 100,000, whereas we calculated an age-adjusted rate for 2024 of 101.7, while the crude rate was 126 per 100,000. So when we look at crude rates, the 2024 mortality rate was higher, but when we look at age-adjusted rates, the 2004 rate is higher. Let's go through another example of direct age adjustment using the total of two populations as the standard. Again, we're going to add the total population from the earlier time period to the total population from the later time period, and that will give us the total population in our fictitious standard population. We're going to repeat that for each age group. Then we're going to multiply the 2011 mortality rate by the standard population for each age group to get the expected deaths using the 2011 rate. In this case, just like the last one, we're dividing by 100,000 to get the smaller number there. We repeat the same process for the 2018 mortality rate per 100,000, multiplying by the standard population for each age group and dividing by 100,000 to get the expected deaths using the 2018 rate. Then we add up the expected deaths using the 2011 rate and the same for the 2018 rate, and that gives us the total expected deaths in the standard population. To calculate the age-adjusted rate for 2011, we divide 13,294 by the total standard population. And for the 2018 age-adjusted rate, we divide the expected deaths using the 2018 rate, again by the total standard population. Indirect age adjustment is often used when you don't have a good comparison group for your exposed group. This is often used in occupational health studies, where you want to study a group of miners or factory workers, and you need to apply rates for a condition from the general population to your occupational group to determine if their rates are similar to people who are not in that profession. Let's go through an example. You work in a village on the North Slope, and residents are worried so many kids seem to be getting lymphoma since fracking became a common practice at nearby gas wells. Your job is to determine whether the pediatric lymphoma rates among local residents exposed to hydraulic fracturing ingredients are comparable to what would be expected in an unexposed population. You have the lymphoma incidence rates by age group for the U.S. population, and you have the age distribution of residents in your village. For each age group, we multiply the lymphoma rate in the U.S. by the local population to get the expected cases if the local population's risk was the same as the U.S. We repeat this for each age group, multiplying and then dividing by 100,000. Then we add up all the expected cases, and we add up the observed cases from each age group. Then to calculate standardized morbidity ratio, we divide the observed cases by the expected cases and multiply by 100. So in this example, we could interpret our result as local kids have a 1.37 times higher risk of developing lymphoma compared to the general U.S. population. If our result had been less than 100, that would indicate that our local pediatric population has a lower risk of lymphoma compared to the general U.S. population. To review, for direct age adjustment, we need to know the age-specific rates for mortality, or whatever the outcome is, of both the exposed and the standard population. For indirect, we only need the mortality rate, or incidence rate, or other outcome of a standard population. In indirect age adjustment, you apply the rates from the general population, or an unexposed group, to a study population. An expected number of deaths is the number of deaths you would expect to observe if the standard population had the same age distribution as the exposed population. And you can use the same adjustment process for factors other than age as well. Let's go through a few practice problems to check your understanding. Age-adjusted death rates provide a hypothetical death rate that would have occurred if the observed age-specific rates were present in a population whose age distribution is that of the standard population. True or false? True. It's important to remember that adjusted rates are fictitious rates you're creating in order to make a comparison between two populations. A standard population created for the purposes of age adjustment doesn't actually exist anywhere in the real world. So you can't use those rates for any other purpose besides making a comparison between those two specific populations. If the outcome is death, direct adjustment yields a standardized mortality ratio. True or false? False. It's indirect adjustment that yields a standardized mortality ratio when the outcome is death. Age adjustment is needed to make comparisons between two populations with different age distributions. If mortality rates from a population with lots of young people are compared to mortality rates in a population with lots of elderly people without first performing age adjustment, the data will be skewed, so it will appear that the older population has higher mortality than they really do, but that's just because older people are expected to die more frequently than younger people. True or false? True. That's why we perform age adjustment in a nutshell. It allows us to accurately compare mortality rates or other rates between populations that differ in their age structure. In epidemiology and related fields, the term crude rate means a rate that has not been age adjusted. This is an important term to understand because you're going to see it when reading epidemiology studies and if moving forward to more advanced epidemiology coursework. When you're reading an article or looking at data in a graph or a table, it's important to take note of whether it's displaying crude rates or age-adjusted rates. You have to make sure you understand what a graph is actually showing before being able to correctly interpret that information.